Yeah, so if you have any doubt, you can start now. Start asking from week 11. Any doubt? So have you started solving week 11 or like? Hello, am I audible?
Yes, sir.
Okay. So any specific doubt you want me to discuss or any concept?
So I have a doubt on activity 11.3, question 2 and 3. I'm not very clear what exactly is conveyed.
Sorry, 11.3.
Question 2 and 3. Yeah.
Question 2 and 3.
Yeah.
Yeah, so you have a matrix, right?
Yeah.
In the question number. So it's basically, see, matrix has a usual multiplication, right? So if I pick a matrix, right? 1, 2, 3, 4, right? And let's say B is a matrix 5, 7, 8, 9, right?
Yeah.
So there is a definition for matrix multiplication. That is the normal definition, right?
Yeah.
Usually,
Yeah. Row into column.
you just multiply this one.
Yeah. Row
with
into
this.
column. Yeah.
And this will, of course, this will give you a 2 cross 2 matrix, right? Right. This is precisely, this is how you multiply matrix in question number 1, right?
Yeah, that was done.
That is fine. Yeah. So the thing is, but here we are doing slightly different thing, right? To find this, so we have a adjacency matrix, right? Which basically tells you what? It basically tells you the path, right? If there is a edge between I and j, then this basically it's 1, right?
Yeah.
So are you getting my point? So if I take this, let's say I have some I, j, k, let's say L, M, and similarly, let's say I'm basically taking the question that you have asked, J, K, L, M, right? And this is 0, alpha, 0, 0, 1, right? And this is 0. Just let me know if I'm writing anything wrong. 1, 0, 1, and 0, 0, beta 1, 0, 0, 0, 0, 0, 1, and this is 0, 0, 0, 0, right? So this is what? This is the adjacency matrix, right?
Yeah.
So what basically this matrix tells you? Basically tells you that if I have a edge from I to, let's say, so this is basically 1, right? That means I have a edge from j to k, right? And if there is no any edge, then you say the for example, it basically saying this is 0, right? That means there is no edge from j to I, right? So this part is clear to you, right? How?
Yeah,
so how?
yeah.
How? So the next thing is, so this when I'm saying this edge, that means I have a length 1. Okay, so I have a path of length 1, right? So when I'm saying that this is 1, then this basically tells you I have a length of I have a path of length 1, correct? So if I take the a square, okay, so next thing is if I compute this a square, then basically this will tell me the length, the path of length 2, right? This, if I compute the a square, and there, so when I'm computing this a square, so here the multiplication is slightly different. Okay, so I am using some slightly different multiplication, that is slightly different multiplication and as well as addition, right? This logical, this Boolean values, right? So you know that this logical OR, logical OR, which basically tells what? If I add 0 plus 0, this basically 0, because both the things are false. So then the final result is also false, right? Then 0 plus 1, it's 1, okay, and which is also 1 plus 0, right? And 1 plus 1 is 1. So as you can see, this operation is slightly different from our usual addition and multiplication, right? And similarly, you have this AND, right? 1 cross 1 is 1, and 0 cross 0 is same as 0 cross 0, same as 1 cross 1. So when I'm computing a square, okay, so what I'll do now, instead of applying this normal rule of addition and multiplication, right, I have to use this one. Okay, I have to use this one. So this rule, basically it will give me the path of, say, using this rule, if I compute a square, right, then this will give me the path of length 2. Okay, so let's compute a square. What is a square? So can you tell me what will be the a square? Okay, so this is a, right? So I have to multiply this matrix with itself, right? So what will be the components of a square? Let's say, so this is my a, and so this is your a, and let's compute a square. Again, for a square, I will have I, j, k, l, m, right? So what, for this one, what I should do? I should multiply this thing with this one, right?
Yeah.
So in that case, I will get 0, correct?
All of zeros.
Yeah. So for this thing, I should multiply this row with this column, right? So in that case, what I will get?
For ij, it has to be alpha.
No, what you are going to do here? You need to multiply this one, right, with this one, right?
Yeah.
First row,
0, sir.
again we'll get 0, right? See what we have: 0, alpha, 0, 0, 1, and you are multiplying with alpha 0, 0, 0, 0, right? So this is 0, this is 0, this is 0, this is 0, and this is also 0, right? So this is also 0. And for this k, what you will get? This ik. So here you will get 1, right? We are basically multiplying this one with this row with this column, right? And again you will get 0, and here I guess you will get alpha, right? Just let me know if I'm making any mistake. Just let me know. Okay. So are you with me? Yeah. So this again, the same thing I will do, right? I'll multiply this. I'll do the same thing with the second root, right? If I multiply this, then what I will get? I'll get 0, right? Again, I will get 0. I'll get beta, right? Yeah. Then I'll get 1. And then I will get 0.
So in the previous case, we should get alpha, no, for K?
Which one? This place?
Yes, sir. In the previous row,
Hmm.
for K, it will be alpha, no, sir.
So instead of you are saying beta, it should be alpha.
No, sir, on top.
Here. This one.
Yes, sir.
So
That's a multiplication with 0.
no, this
Alpha.
what you are doing. You are multiplying this one, right? With this one. Right? What you
Yes,
should
yes.
get. It should
So
be
alpha into 1, no, sir.
no. Okay. Yeah, correct. Now it's fine.
Yes, sir.
Yeah. So again, like similarly, okay. So this is just a matrix multiplication. So so what actually we are doing here? So as you can see, we are actually using this rule. Okay, this logical operation. Okay. So let me write what I am doing. So let's say if I multiply this one, let's say if I multiply for this entry, okay. So for this entry, if I need to multiply this one with this one, right? So what I will get? I will get 0 plus alpha again I will get 0 and again I will get 0, again I will get 0, right? Correct or not? Hello?
Yeah.
So the thing is, as you can see, so if my alpha is 1, okay, if my alpha is 1, then I will get alpha, right? Because of this logical OR, right? Because 0 plus 1 plus 0 plus 0 plus 0, right? So this is 1 and this whole sum is 1, right? And if my alpha is 0, still I will get 0, right? So what I am saying, so instead of 0, if I will have a 1 here, okay, instead of 0, if I am making some sum, let's say I'm getting alpha plus 0 plus 0 plus 0 plus 1, right? So what will be the value of this sum?
1.
What will be the value of this sum? This sum will be 1, right?
1. Yeah.
Because see, alpha plus 0 is alpha. And eventually you will get alpha plus 1, but it doesn't matter. See, alpha has two possible choices. Alpha can be either 0 or 1. But it doesn't matter what is the value of alpha, because if I add alpha with 1, then according to the rule, 0 plus 1 and 1 plus 0 or 1 plus 1, they're always 1. Okay. So the point that you need to understand that when you are multiplying this adjacency matrix to get this A square, you need to apply this operation. Okay, you need to apply this operation, then only you can get the A square. Okay, and once you get the A square, then from there you can get the value of the so basically, yeah, it's asking what will be the value of alpha and beta. Okay, once you multiply A square, from here itself you can compare, right? It's given that a square is this. Okay. So from there itself you can say that alpha is, so here you are getting alpha, right? So if you compare, it's basically in this position, you have 1, right? So alpha is 1 and beta, you can say it's 0. Clear now?
Yeah.
So the main idea is when you are trying to find a square, always apply this one. Okay. So at least see, this is, as I said it before, this is not the usual matrix multiplication. Okay. We are actually applying this rule, this logical or and this one and operation. Okay. So here the addition and multiplication, they're slightly different. Okay. Is it clear?
Yeah.
Okay. Okay, anything else? Any other doubt?
In activity 11.4 also, in question number 1, the last sentence is marked as true. How is that? 11.4. Question number 1, there are multiple sentences, statements. Yeah. So in that, the first 3 fine, but last sentence, shortest path in a weighted graph need be minimum in terms of
Edges, correct, right?
Yeah.
Correct. In a weighted graph, yeah. This is a correct statement, right? Shortest path in a weighted graph need not to be minimum in terms of number of edges, right? Because in a weighted graph, how basically you compute the shortest path? It's depends on the edge, right? Suppose you have a.
Yeah, you are looking for the least values for the.
So
the least weights.
Yeah. So this is suppose 1 and 1.
Okay. Yeah, got it.
This is 10, right?
Yeah.
So it's depend on the weight of the edges through which you are traveling.
Yeah. So you may select large number of edges. Further adds to even a smaller number than a direct connect. So
yes. So in terms of edges, this is shortest. Okay, because you are basically traveling only one edge, but in terms of weight, this is not the shortest because this is the shortest path. Okay, because here you are actually spending 2 units, and here you are spending 10 units. Okay. Clear?
Okay. Yeah. Agree.
Yeah. Okay. Anything else?
Yeah. Sir, I have a doubt in 11.6, question number 3.
Question number
3. Yeah, I also have. Yeah.
So here they have given the graph and said the value of x. Can we use the Bellman-Ford algorithm to find the shortest path from a source vertex, which is 0, to every other vertex in the graph given below? So I think the x is applicable only to vertex 4. So based on my calculation, it should be -6 because from 0 to vertex 1, it is 6, weight is 6. So if we counter it by -6, then it becomes 0. That was my understanding, but the correct answer seemed to be -7, infinity. So I couldn't understand that.
Yeah, so basically, so the thing is, okay, I guess you understand the logic. Like, when you can apply this Bellman-Ford algorithm, when you have no
negative weights. Right?
Yeah, negative
cycle.
Yes.
Right? Yeah.
So again, see the thing is, again, like if your cycle is also 0, right? That is also not there is no point, right? If you have a 0 cycle. Right, because you can simply move around the cycle and it's not going to create any problem, right?
Yeah.
So in that case also there is no point, right? So if I have a graph, okay. So suppose I have a graph, okay. So if I have a graph and here all the edges are actually weights are 0, okay. So this is simply a graph, right? I can't say that this is a weighted graph, right? So there is no point of considering a cycle of total weight 0, right? So you have to always consider the length, the total weight of the cycle to be positive.
Hmm.
So now this is your cycle, right?
Yeah.
So what you want? You want the length, the total weight of the cycle to be positive, right?
Right.
So that means 3 plus 4 plus x should be greater than 0, right?
0. Yeah.
That means 7 plus x should be greater than 0, right? That means x should be greater than -7, right? So if x is greater than -7, then the length of the total weight of the cycle will be always positive, right? So if you take x to be greater than -7, then actually you can apply Bellman-Ford algorithm here. Okay, so that means the range of x is basically in between -7 to infinity.
Oh, okay. Okay. Got it. Okay. So -6 fits in there, but okay. This is a range. Okay.
Yeah.
Got it. Got it. Okay. Okay. Yeah. One more doubt I
Yes.
have on that is on activity 1. It's 11.8. 11.8. Question number is 3. Yeah. How many spanning trees are possible from the graph shown in figure?
So let just a minute. This is impossible for me to draw all the graphs. So I'll say the question. You can see the question, right?
Yes. You can see your screen. Yes. Number
So,
3.
Yeah. So okay. So I'll suggest. Yeah. You take a
number
picture
3.
of.
It's the previous question. Yeah. How many?
Okay. So.
Yeah.
Okay. So
actually,
you are
it's continuation of 2. Yeah. It's continuation of 2.
Okay. So then in that case,
This graph. Yes.
Yes. So this is the graph, right?
Yes.
0, 1, 2, 3. Okay. So in that case, I can let me draw the question. I thought the next question. Okay. So this is okay. I'm not giving any number because again, it doesn't matter. Okay, so let me give 0, 1, 2, 3, 4, 5, 6, right?
Yeah.
So,
yeah.
So you want a spanning tree, right? So you have, so here you just concentrate on this part. Right. So I have 4 edges here, right?
Yeah.
So if I remove any 2, it's not going to create any problem, right? If I remove any 2, it's not going to create any problem, right?
Yes.
And
yes, correct.
at the same time, okay, at the same time, I can remove any one of these 4 edges, right?
Any one of, yeah, okay.
Any one of the 4 edges. Suppose I remove this one and this one. What I will have? I'll have this graph, right?
Yes. Yes.
Right?
Yes.
Am I making any mistake?
No, sir. It has coverage of all vertices.
Yeah. Okay. So yeah, so this is the spanning tree.
Yes.
Yes. Right.
Yes.
Okay. So if I remove this one and this one, no, then it's going to create problem, right? If I remove this one and this one, it's going to create problem, right?
Yes, yeah, you can't remove the one above and below simultaneously.
But I can remove this one and this one, right?
Yes, you can remove that. Yes.
And
Yes.
I can remove this one and as well as this one, right?
Yes. Yes.
So okay, so what actually just give me a minute, let me think. So if I keep this one like this, I keep this one like this and like this, right? So I can, in that case, I can remove this one, right? So how many edges I have? 1, 2, 3, 4, 5, 6, 7, 8, right? So if I, what is this number? 8 factorial. 6 factorial into 2 factorial, right? So this is what? This is 8 times 7, basically by 2. Okay. So, but again, still I will have problem. Still, so if I remove this one and this one, whether it's going to a spanning tree.
Which two, sir?
I'm saying this one and let's say this one.
Yeah,
Yeah, you can have a
It
spanning
won't
tree.
be-
Yes.
right click path. Yeah.
Yeah, just a minute.
So I think any one edge from left and any one other edge from right.
Right. Yeah.
Yeah.
So that is the main idea. So yeah, that is what I'm checking whether this basically makes sense or not. Okay. So yeah, so basically the thing is, if you remove any one of, so you have 4 edges here, right?
Yeah.
So here you can remove any one, right?
Yes. Yes.
And here also you have 4 edges, right? So here actually you can remove anyone.
Anyone. Yes.
But the thing is, if you remove, so and also you have to make sure that if you remove 2 edges from this side, okay, then it will be a disconnected graph, right? And similarly, if you remove 2 edges from this side, it will become a disconnected graph. Okay.
Yes.
And if you remove 1 edge here and from here, still it is a connected as well as it's a tree, right? So that's why the total possible ways is basically 4 times 4, right? Which is 16. So here you have 4 choices,
Okay,
right?
okay.
In this side you have 4 choices, right? You can remove 0, 1 and 3, 4. You can remove 0, 1, 3, 6, 0, 1, 6, 5, 0, 1, 4, 5. Okay. Similarly for other also, right? So the total number of possible choices is basically 4 times 4, which is 16.
God. Okay. Okay. Got it, sir. Yeah.
Yeah. Okay.
One
so this
final.
yeah.
So one final doubt, that's a general doubt. See, we have come across several algorithms in this week, right? So starting from Bellman's, and ending with the last two, right? The
Prim's
Kruskal's
algorithm and Kruskal's
algorithm.
Yeah.
So the solution to the problem for which we are solving using the initial algorithms can also be solved using prims and Kruskals, right?
Yes, true.
Yeah. Then is there any specific reason that we have to? I mean, basically, I want to understand that this algorithm should be used when a problem comes with this. I mean, we understand that if there are negative weights, we can't go and use the initial one that I will tell the name, the fire method.
Yes.
So that algorithm cannot be used if there is negative weight. So those differences we understand, but in general, in all other cases, we can even apply the prims or Kruskals, which seems to be much simpler compared to the previous ones for me. So but is there any reference table or something that is available where we can differentiate for this kind of problem? We have to use this particular algorithm.
No, it's okay. So there are, you are basically in many sense, actually, it's depend. There are, so when you are you are not going to compute all these things on your hand, right? Of course, we are doing it, but in some small scale. Okay. So, but again, like it's matter also there is a complexity issue, right? So which one is giving with some complexity and which one is giving you more complexity. Okay, so that also plays a role, right? So it's depend. So I'm not sure like what is the complexity of this Kruskal algorithm. Okay, but the thing is, okay, I feel this okay, so I feel this Kruskal algorithm is slightly better, right?
Yeah.
Because okay, so the idea is you in some sense you
choose the least weighted things and least connect them.
Yeah. So I'm not sure the much difference of this Prince algorithm and Kruskal algorithm in terms of complexity. Okay, so this complexity actually plays a huge role. Okay, when you are talking about algorithm, this complexity actually plays a huge role. Okay, so your algorithm is, so when, in what sense actually you say the algorithm is better? Okay, so in the language of computer, when the complexity is less, right? If you are applying the Kruskal algorithm and it's taking half an hour, whereas this Prim's algorithm it's taking 1 hour. So then it's completely depend on the complexity. On that basis, actually, you can say that okay, this algorithm is better, this algorithm is comparatively okay. So so in that sense, actually, you can say. Otherwise, see, of course, there can be multiple ways of doing a single thing, right?
Yeah.
And for example, this flawed Warcel algorithm, okay, and whereas this, if you talk about this the single source shortest part, this what is that algorithm?
Dijkstra.
Dijkstra. So in
Bellman-Ford.
Yes. So Dijkstra algorithm you can't use for negative weight, right? And whereas this Bellman-Ford you can use for negative weights. Okay.
Yeah.
So there are some advantage in terms of this. Okay. But I don't see much difference in Kruskal algorithm and Prim's algorithm.
Yeah, between Prims and Kruskals, I understand, but between this one Bellman's and Kruskals or Prims, I see a lot of a lot of time would be saved if we go for Kruskals or Prims, right? Because here you have to go path by path, but ideally, this one is you have to start from a source node and go forward. But there in Kruskals or Prims, it's like all point.
But here actually it's giving you slightly more information, right? In Bellman-Ford's and particularly Bellman-Ford's, or even if you talk about this flawed Warcel algorithm, it's also giving you this the transitive closure of the matrix, right? So which you can't get in Sprint's algorithm and Kruskal algorithm, right? So it's not
Okay.
only about the path. See, you have to see what are the information you can get out of it. Okay. So for example, this Floyd Warshall algorithm, you actually this basically gives you the transitive closure, right? And it's a huge information, right?
Yeah. Yeah, got it. Okay. The amount of information we
Yeah,
derive. Okay.
yeah,
Yeah.
that also matters. Okay. It's
Got it,
basically
sir. Thank you.
yes.
Yeah. Yeah, I have one doubt. That's on activity, week 10, question number 2.
Week 10.
No. So the 10th week 11.10. Sorry. 10th class.
Yeah.
Week. Question number 2. The thing is, see, there are 4 statements. It's more about, how do we really, find it out rather than doing some kind of, visually go through each of the options and then try to answer that, or because I noticed when you solve the previous question on this number of that when we arrived at that 16 number using a it was more like using a formula rather than trying it out. So
which one?
No. My question is that my doubt is about 11.10 other statements in question number 2. Minimum cost spanning tree of graph G is unique. Then the second statement is there can be more than one minimum cost spanning tree of the graph G because there are some edges with equal weights. There are 2 edges with equal weights, 1 and 3 in that. Not 2, actually 3, 4 are there, 5, 5, 4, 4, like that. So even then the answer is given as wrong. Whereas in this lecture, you are telling if there are because you can use different.
No, so yeah, exactly. See, the thing is that there is difference. See, path can be different. Okay. But but what it's asking, the minimum cost, right? So eventually what you are computing, we are computing the total cost, right? So for example, if I take this graph, okay, if I take this graph, so if I again this 1 and 1, let's say 1 and let's say 2, and let's say this is 2 and 1, right? So I have 2 paths, right? I have 2 paths, right? This one and another this one. Okay. So the path, the sequence can be different, right? So if you apply some, let's say Prim's algorithm, right? So you may get A, B, C, right? Or you may get A, D, C, right? But the total weight, if you compute the total weight, okay, but this is also 3, this is also 3. Okay, so this what actually this asking, it doesn't matter on what path you are traveling, what is the total weight, okay, what is the amount of what is the total amount we are spending on that path. So this is always same. Okay, so
it was a wrong understanding on my side. The path also has to be, say for example, ABC. So the focus here is purely on the cost involved.
Yes, the cost involved.
Okay.
Basically we're finding the minimum cost spanning tree, because if the cost is not unique, then there is no point of this algorithm. Okay, this is both the algorithms are basically sort of pointless, because if it's not giving you the unique cost, then no point of applying that.
But if you look at the second statement, more than one minimum cost spanning tree of graph G. So what does that really convey? Means minimum cost can remain static, but there can be multiple graphs, right? I took it like that. That is why
okay. So so maybe
because that wording.
In some sense I agree, but so this wording is maybe problematic. but
Yeah, it can be
yeah.
little more, I think, explicit.
Yeah. So, but yeah, so the main idea of the question is that it's basically asking the overall weight. Okay. Yeah. We will try, yes, slightly. We'll try to slightly modify.
Yes, that is, yeah. That's it. Yeah, and just one more observation is that the solution with us week 11 in that, there is nothing in that.
Sorry.
Solution, see, between practice assignment 11 and graded assignment, there is menu given solution, solve with us week 11. There is nothing. I could not find anything when I clicked.
Okay. So tomorrow actually there is a solve with us session.
Okay. So after that only it will be uploaded.
Yeah.
Okay.
After that we'll upload.
Okay. Great. Yeah.
Okay. Any other questions?
Yeah. From me, no.
Yeah. Any other question from week 10 or 11?
Sir, week 11 is the last content for this term, is it? Okay.
Yes. Week 11 is so there is no content for week 12.
Okay.
Okay, so again, like if there is no question, then probably I'll stop here because
So nothing from me. So thanks for the clarifications.
yes, okay. If there is no question, yeah, then probably I'll stop. Okay. So yeah, tomorrow actually there is solve with us session. So they will discuss a bunch of questions, and after that we can upload that slide.
Okay.
Yeah. Okay. Thank you.
Thank you, sir.
Thank you, sir.